Imagine you have a sheet of paper with a drawing on it. If you slide the whole sheet left, right, up, or down, the picture moves exactly the same way. This is called translation. If you spin the sheet around a point like turning a pizza on a plate, the picture rotates. This is rotation. If you stretch the sheet like pulling on a rubber band, it gets bigger or smaller. That is scaling. In computer graphics, we need these moves all the time. A game character must walk across the screen, translation, a wheel must spin, rotation, and a map may be zoomed in or out, scaling. They let us change where something is, how it is oriented, and how big it looks without redrawing the shape from scratch. A point in 2D can be written as a vector x, y. To move that point, we can use a matrix. X prime equals a x plus by, y prime equals cx plus dy. If we want to translate, we cannot do it with just a 2x2 matrix, because multiplication can only scale or rotate. Instead, we add a separate vector t sub x, t sub y. X prime equals x plus t sub x, y prime equals y plus t sub y. Translation, add t sub x, t sub y to the original vector. Rotation, multiply by a matrix built from cosine and sine of the angle. Scaling, multiply by a matrix where the diagonal entries are the scale factors, for example s sub x and s sub y. These simple algebraic forms let a computer turn geometry into numbers it can compute quickly. To handle translation together with rotation and scaling using only one matrix, graphics uses homogeneous coordinates. We add a third coordinate set to one, turning xy into xy1. Now a single 3x3 matrix can do everything. X prime y prime 1 equals a bt sub x, c dt sub y, 0, 0, 1 multiplied by xy1. The top left 2x2 part still does rotation and scaling, while the rightmost column t sub x t sub y adds translation. The bottom row 0, 0, 1 keeps the homogeneous coordinate unchanged. This trick lets us treat all 2D operations uniformly and combine them by simple matrix multiplication. Suppose we want to rotate a point by an angle theta around a special pivot point P equals P sub x, P sub y instead of the origin. First, we move the pivot to the origin, rotate, then move it back. In formulas, translate the point so the pivot is at the origin. X, y maps to x minus P sub x, y minus P sub y. Rotate with the standard rotation matrix. R theta equals a matrix with first row cos theta minus sin theta, second row sin theta cos theta. Translate back, add P sub x, P sub y again. Putting the three steps together into one homogeneous matrix gives M equals T of P sub x, P sub y times R theta times T of minus P sub x, minus P sub y, where T is a translation matrix. Expanding the multiplication results in a single 3x3 matrix whose entries contain cos theta, sin theta, and the pivot coordinates. This matrix can be used on any point to rotate it around the chosen pivot in one step. The intuition is like holding a compass at a point on a map and swinging the needle around that point. You first bring the map to the needle, spin, then put the map back. Scaling changes the size of objects. A uniform scale uses the same factor s for both x and y. S sub u equals a matrix with s in the top left, 0 in the top right, 0 in the bottom left, and s in the bottom right. A non-uniform scale uses different factors s sub x and s sub y. S sub nu equals a matrix with sx in the top left, 0 in the top right, 0 in the bottom left, and sy in the bottom right. If we want to scale relative to a point other than the origin, say the center of a sprite, we translate the point to the origin, scale, then translate back just like rotation. M equals T of Cx, Cy times S times T of negative Cx, negative Cy, where Cx, Cy is the chosen center. Think of it like holding a picture frame with your fingers at a corner and pulling the frame. The corner stays where your fingers are, the pivot, while the rest of the picture grows or shrinks around it. When we need to do several moves one after another, for example, move a character, then rotate it, then make it larger, we can concatenate the matrices. If we have matrices A, B, and C for three operations, the combined effect is M equals C times B times A. The order matters because matrix multiplication is not commutative. The rightmost matrix A is applied first to the point, then B, then C. In practice, we build one big matrix once and use it for every vertex, which saves a lot of work. As an analogy, think of stacking three transparencies on a table. The topmost one, the rightmost matrix, is the first thing you see, but mathematically it is applied last. This technique is called transform hierarchy, and is why hierarchical models like a robot arm work. Each joint has its own matrix, and the final position of a fingertip is the product of all joint matrices. In modern graphics pipelines, the vertex shader receives the position of each vertex as a 4D homogeneous vector for 3D, but the idea is the same for 2D. The shader multiplies this vector by a model view projection matrix, MVP, that contains all the transformations: translation, rotation, scaling, camera view, and projection. Uniform mat 3 U transform. In vec2 A position. Void main open brace vec3 pose equals vec3 A position, comma 1.0 semicolon vec3 transformed equals U transform times pose semicolon GL position equals vec4 transformed dot xy comma 0.0 comma 1.0 close brace. The pixel fragment shader usually does not apply geometry transforms. It works with the interpolated color or texture coordinates that were already moved by the vertex shader. However, some effects like screen space distortion may apply a 2D matrix to texture coordinates inside the fragment shader. The entire pipeline, vertex fetch to vertex shader to primitive assembly to rasterizer to fragment shader, uses these matrices to turn model space coordinates into screen space, making the object appear where we want, how we want, and at the size we want. Computers store numbers as floating point values which have limited precision. When we multiply many matrices, tiny rounding errors can add up, causing objects to drift or wobble. To keep things stable, use single precision float for most real-time graphics because it is fast, but avoid extremely large or tiny values. Keep coordinates near the range -10 to the fourth to 10 to the fourth. Pre-multiply all static transforms into one matrix once rather than applying many small matrices each frame. When rotating many times, accumulate the angle as a single value and recompute the matrix instead of repeatedly multiplying rotation matrices, which can gradually lose orthogonality if you must accumulate ray orthogonalize the matrix with Gram-Schmidt or by normalizing the basis vectors. Use SIMD instructions like SSE and a VX or GPU native matrix multiply instructions to get both speed and consistent rounding. Performance tricks. Store matrices in column major order. If the shader language expects it, reduces transposition work. Pack several small transforms into a uniform buffer so the GPU can read them all at once. Skip transformations that are identity no change to avoid unnecessary multiplications. By paying attention to these details, we keep the visual result crisp and the program running fast even on devices with modest hardware.